Okay, what I want to do in this video is I want to show how the original way Archimedes was able to discover the volume of a sphere. I just see now that maybe needs to be a little more filled in. So the method that I'm going to go over is his method. I believe it's his initial method. That's what historians are saying, that this was his initial method, unlike maybe later methods that were uncovered or that were more known. This method was not uncovered until the beginning of the 20th century. And it is a method of exhaustion, and there might be some details here that he skips and that we skip that I sort of mentioned in the previous video about being careful about things. But I'll let you sort of work those things out on your own. Okay, so this is the method that he did. Now, he came up with this method. It's a very interesting method. It's not at all the kind of ways. It's not at all how I would think through this problem, but it's how he thought through this problem. And his basic idea, and he uses this method a lot. This is one of his main methods. Is about balancing things on a lever. So imagine, for example, we have some lever here, and we have a fulcrum here. He knew that if you have a mass here and multiplied it by its distance from the fulcrum, it would balance a mass over here if the product of the mass and the distance here equals product of the mass and the distance here. So you can set up an algebraic equation. If you have things over here that you know the mass and distance of, and some things over here that you know the mass and distance of, or you know the balance and that sort of thing, then you can solve for the variables. So I will explain what all of that is in just a moment. But here's how he began. He starts by drawing, imagining, so this is a top half of a sphere. He starts by imagining a cone like this that's inscribed in the sphere. So the vertex is here at the top of the sphere. The line goes down like that. This is not a color of green that I'm used to seeing out of this marker, but it seems like it's showing up okay. And then we're gonna have this, okay, a little not so good of a drawing over here, but the left side's not gonna matter. Let me make it a little bit darker. And then what he imagines is, okay, so now here's where the scale is gonna go off a little bit. Imagines the following. Let's take a cylinder of radius 2r. So let's take a cylinder of radius 2r. So this right here is kind of the origin. We'll take a cylinder of radius 2r. Let me try to get the scale at least right. So this is going to be 2r here. Again, let me just try to get the scale a little bit correct. We're going to look at a cylinder of radius 2r, and it's also going to have height 2r, but we're just going to look at the top half of the cylinder. So it's going to be just this top half of the cylinder, like this. Okay, so I'm drawing these as two-dimensional shapes, but these are really three-dimensional shapes. Okay. So this blue thing is a cylinder of radius 2r and height r. I think he initially did it by considering, if you look at the whole sphere, the whole cone, the whole cylinder, it would go down here to r. That's minus r down here, and so it would be height 2r and then radius 2r. Okay, now what he's going to do is the following. I need to make sure I'm going to have enough room to write everything. What he's going to do is the following. He's going to imagine a fulcrum, or a lever with a fulcrum. And what he's going to do is he's going to say, if I put the cone here and the top half of the cylinder, so we're imagining that the cone here and the top half of the sphere. So what we're doing is we're imagining that all three of these objects, the cylinder, the cone, and the sphere, are all made out of some uniform material so that their volume and their weight are proportional to each other. Okay, so imagine it's made out of some uniformly dense material of 1 unit, 1 kilogram per cubic meter, or whatever. The units don't really matter here because we're just looking at the relationship between them. Okay, So if you put the cylinder here, the solid cylinder here, and the solid sphere here at a distance of 2r, so this is 2r, a distance of 2r, let me make sure that shows up well, okay? And then if you take the cylinder, so its height is a distance of r, okay? If you take the cylinder and lay it on its side, so lay it on its, like this side right here, so it's going to be, this scale is going to be a little bit off here. This distance here is r, and then I guess this distance here is going to be like 4r or something like that. Okay, if you take it and lay it on its side like that, then these two things are going to balance each other out. Okay, and using what he knows about levers, using what he knows about the volume of the cylinder, and using what he knows about the volume of a cone, he can now solve an equation for the volume of the sphere. Okay, so I want to show how he comes up with this balance idea right here. And I'm going to leave it as an exercise for you guys to show that given that this balancing is true, that therefore we can compute the volume of the hemisphere and then multiply that by 2 and you get the volume of the whole thing. Okay, so again, I'm going to use kind of modern, I don't know if I've said this in this video, I'm going to use modern notation and algebra and things like that. I'm going to use his techniques but translate it into modern language because it's just way easier to kind of use graphs and diagrams and variables like x and axes and all of these sorts of things than it is to kind of use language that he was speaking. The analytic geometry thing is helpful, but I'm going to give his method just kind of in our language. In other words, I'm not just going to like use straight calculus or something like that, but you will see, as we've discussed, it is going to be very calculus-like. So I'm going to draw an axis here, vertical axis, like this. And let's say this just, it doesn't really matter that that's called the x-axis, but I'm going to call it the x-axis. And then this right here is the y-axis. The fact that we're calling that the y-axis is going to be a little more important, but not that important. Okay, and so this is what he does. He says, I'm going to, instead of looking at this problem first, I'm going to do what we recognize as kind of a very standard calculus thing to do. I'm going to break the problem up into slices and look at each slice and see what I can tell about those slices. So what he does then is he takes a slice. Let's say we're going to look at a height here. Let's call it y. And I'm going to slice. And I'm going to slice. Okay, so again, these are three-dimensional objects. So when you slice them, and really it's more like a chunk that we're taking out. So you cut here, and then you cut right above it or something, and you get a slice. You get like a disc. Okay. So what are we going to get? When we take a slice of the cone, that's going to be the smallest circle. It's going to be a disc like that. When we take a slice of the sphere, it's going to be a little bit bigger. It's going to be something like this. And then when we take a slice of the cylinder, that's going to be the biggest one, and it's going to be something like this. Now, I want to compare the weights of each of these discs. Now, we're going to assume that they all have the same thickness. They all will have the same thickness, and we're just going to call it, for whatever, however you want to call it, we'll just call it delta y. That's not going to be so important. And so the weights of each one of these, discs is basically going to be its area times delta y. Well, they're all discs, so we know how to find the area of a disc. It's just pi r squared. So now we just need to figure out what the radius of each one of these shapes is. Okay, so how can we do that? Well, let's notice that we've got some similar triangles happening here, and maybe we can use that to find the radius of each one of these things. Well, the distance from here to here. So let's look at the distance from here. Let's look at the radius of the green. The radius of the green disk is going to be the distance from there to there. Okay, so let's see if we can think through kind of in terms of triangles what this is going to be. Well, notice this green triangle here is an isosceles triangle because it's a right angle. This distance is r and that distance is r. So it means that these two side lengths are the same. So this side length and that side length are the same. Now the total distance up to here is r. That got erased or it was never there. This distance is r. This distance is y. So this distance is y minus r. This distance right here is y minus r. And so this distance right here is y minus r. So the area of this is going to be pi times y minus r squared. Pi times y minus r squared. Okay, now what about the purple? Well, we're going to have something similar going on with the purple. If you look at the purple, the radius is going to be the distance from here to here. Now let's look at this triangle. So now we have another right triangle. Okay, so what can we do with this information? Well, we know that this distance here, that's the radius of the sphere. So the distance from there to there is r. And we know that the distance from here to here is y. So I'm looking at this triangle here. So let me put some purple here. So I'm looking at this triangle here. This is a right triangle. The hypotenuse is r. This side length here is y. So now we can do a little Pythagorean theorem to figure out what that distance is here, this distance. Okay, so we know that y squared, that's this distance, plus, I'm going to call this just d squared, plus d squared has to be equal to r squared. Okay, so what it tells us is that d squared is equal to r squared minus y squared. D squared is equal to r squared minus y squared. So the area of this is going to be pi times, I'm using d to mean a radius, which is probably not the best choice here, but whatever. It's going to be pi times d squared, which is r squared minus, r squared minus y squared. Now for the blue circle, that's the biggest one. And notice that the blue circle is always going to have a radius of 2r. So this area is pi times 4r squared. Okay, 2r squared is 4r squared. Okay, so this is what Archimedes does. What he does next is he says, okay, well, let's imagine if I place the green disk here, so its center of gravity is at 2r, and I take the purple disk and I put it here, so its center of gravity is at 2r. Where do I need to place this blue disk over here? Where do I need to place this blue disk over here so that these two things balance? Because we know the weights of everything. So what do we know here? I know the mass times this distance. I'm going to call this distance A. I know the mass times this distance has to equal the sum of these two masses times that distance. So the only thing that I don't know about in this diagram is A. And so now let's just do a little bit of algebra over here. So what do I get when I add these two masses together? Well, when I multiply this out, we're going to get pi times y squared plus r squared minus 2 pi r, or minus 2yr. And notice what happens when you add them together. The y squared cancels with the y squared. And so what we're going to have when we add these two masses together, what we're going to get is pi The y squared is canceled. 2r squared minus 2yr. Pi r squared minus 2yr. Okay, so that is the mass times delta y, we should say. That is going to be the mass of these two things together, and the mass of this over here is going to be pi r squared times 4, and then delta y. As you're going to see, the delta y is not going to matter here. All right, so now a times this is equal to 2r times that. So a times this is equal to 2r times that. So let's try to figure out what's going on here. So I'm gonna erase everything because I need to do a little bit of algebra here. So again, for these two things to balance, a times this, so a times 4 pi r squared, man, delta y has to equal to 2r times this, has to equal to 2r times pi times 2r squared minus 2yr delta y, like this. Okay, so let's start doing some algebra. What can get canceled here? Well, I have a pi. This pi can cancel with this pi. Notice over here, let's do a little in-place editing here. I can factor out an r. Factor out an r, it comes as an r squared here. So this r squared cancels with that r squared. I can factor out a 2. So this 2 is going to come out as a 4 here. And now these 4's can cancel. And of course the delta y's can cancel. So we've canceled everything out. On the left hand side we have a. And on the right hand side we have r minus y. And again, I realize as I'm doing this that my variable names are probably optimized to be the most confusing, because I'm talking about areas, and a here is not an area, it's a distance. But what it tells us is that this distance needs to be r minus y. This distance here needs to be r minus y. So let's think about what's going to happen here. We're going to start from y is equal to 0. And we're going to cut. So conceptually, what's happening? If you want to think about putting the cone and the hemisphere here and the cylinder here, so that they balance, here's what's going to happen. We can take a slice, when y is very small, like when y is equal to 0. We're going to put the slice of the cone and the slice of the cylinder over here. And where do we need to place the slice of the cylinder, the slice of the cone and the slice of the sphere over here, and where do we need to place the slice of the cylinder so that it balances? Well, it needs to be at approximately r. If y is approximately equal to 0, it's going to be approximately r. Now, as y increases, what's going to happen? Well, we're just going to keep stacking everything. The cone and the sphere are going to keep getting stacked right here in the same position. But what's happening over here, the cylinder is going to get closer and closer. As y increases, we're going to be stacking things, closer and closer this way. Okay, so again, what's going to happen then is we sort of move linearly up in y this way. We're going to be stacking slices of this cylinder this way. At each new position, we're going to, if we can think about discretizing the y-axis here, we're going to be putting slices of the cylinder. And eventually, we're going to fill up the cylinder going this way, and we're going to have the hemisphere and the cone here. And they're going to balance after we do this. Now again, this requires a little bit more argumentation. Because, for example, if in our algebra we had found the position here was r minus y squared, we'd still be filling up going to this distance over here, but it would not be like filling up in a linearly, in a linear fashion, where like the amount of cylinder here is the same as the amount of cylinder there. Okay, so there are some issues with this, and perhaps even Archimedes recognized this, because when he sent these letters to people, he was kind of like, well, hold on a second, maybe. Well, I don't think he said hold on a second, but I think he expressed in the letters that I've seen, it seems like to me, he's expressing some sort of like, well, I really wish somebody else could look at this to kind of verify it. In fact, one of the letters, he's like, I really wish this guy that had died could look at it, so he could verify it. But I guess since he's not alive, you'll do second best or something like that. Anyways. So there are definitely parts of this argument that are not quite there, according to our standards, at least the way that I presented it here. Even though Archimedes did have other arguments that were, completely rigorous according to our standards. But I think this is a very interesting idea. And you can see that there's a lot of calculus-like things going, right? This is exactly how we would compute things, using calculus nowadays. In terms of the slices, we would exactly do something like that and then add those all up together. But I guess he didn't have that way of just taking the slices of the sphere and figuring out what those are and then adding those together and taking a limit. That's just not an idea that he had at this point. Though later on, these are the sorts of things, as we will discuss, that he does do. At any rate, I really think this is an interesting way to think about this problem and to try to find the volume of a sphere. Again, we found the volume of the top half of a sphere. And again, I want you guys to finish the proof, finish the argument, that if you have a cylinder going from a cylinder of, as I set up, of radius 2r and height r, going along this part of the lever from this to a distance of r, and the top half of the hemisphere, or the top half of the sphere, the top hemisphere of the sphere, and the cone sitting here. This is unknown. This is known. This is known. But I mean, what I mean is the volume of the cone is known. The volume, or this distance here, 2r, is known. The volume of the cylinder is known, and this distance here, 0 to r, is known. You're going to have to think about where the center of the mass of the cylinder is and how that affects the lever computation. But the only thing unknown here is the volume of the hemisphere. And so you set up an algebra problem where the mass of the cylinder times the distance of its center of gravity to the fulcrum is equal to 2r times the mass, the sum of the mass of these two things. Easy algebra problem. It's going to be one of the homework problems for you to complete that. Anyways, that's it for Archimedes' proof, or computation, I should say, of the volume of the top half of a sphere.